The topic of today's discussion is a product called as ShiftLeft Ocular, analogous to Google Maps for auditing your code with a security purpose. So given that we started the title as Google Maps, all of us are privy to this visual. Every time when we embark on a journey, the first thing we do is plot our source and destination, and thereafter understand various routes available to our dispense to traverse towards our destination. The map also provides us enough contextual information from the perspective of traffic contention, roadblocks, construction, anything that helps us aid our decision-making process of choosing the appropriate route. Behind this map is actually a graph, because you have two nodes and an edge connecting those two nodes. And of course, there are various other edges, great amount of detail, providing you enough context to make the appropriate choice. Now let us zoom into the application that is actually built and is powering those maps and those visual interfaces that we use when we embark on journeys. Every application is written using source code. Engineers write source code because that's their core competence and expertise. And as they write source code, they are iteratively reasoning and coding at the same time. When they code, they write functions, and one function calls the other in order to serve your purpose as you interact in the web browser when that application is hosted. When these applications become relatively complex and we take an aerial view at it, it almost looks like this. It's almost a complex graph of connected edges and connected nodes. At the nodes lie various functions, and once a function is called upon, it communicates with other functions to serve our business needs. Now note that this becomes relatively complex as our application evolves over time. When we deploy this application, our consumers interact with the application, and so does malicious or adversarial entities. The sole purpose of attackers or adversarial entities is to figure ways to exploit our application. Their aerial view of our application is likened to a maze, and they're essentially traversing our application in order to find inherent vulnerabilities that they can potentially exploit and exfiltrate data. Note, as they traverse the maze, they're conducting trial and error exercises. So we looked at three different perspectives, one from an engineer, the other from a security personnel, which is essentially the aerial view of our application. The third is from an attacker perspective. Behind all three of these perspectives are graphs. So let us pause and ask ourselves, why are graphs interesting and used as the core representation behind all these structures? How can we represent code in a graph? Because everything starts at code. Code is written, compiled, packaged, and deployed that becomes an application that our consumers touch. And thirdly, what can we learn from a graph? What are the advantages of having a graph at our dispense? Let us guide our thinking with a model, a very simple representation of an employee working for a company, reporting to a manager, working on a project associated with that company. Any entity that we're speaking of is represented as a node. The relationship between various nodes are represented as edges. And note that nodes and edges have metadata associated with it. As the example states, when we're speaking of an employee, the employee has identity, as in a number, social security number, name, home address, etc. Using this metadata, we can essentially traverse and ask intelligent questions on this graph, like which department does the employee work for? Who does the employee peer with or report to? What are the projects that the employee is working on? Having this graph helps us ask these intelligent questions. Let us context switch to observe how the compiler observes our code. Coincidentally, a compiler also observes code that we write as a graph. Compilation has various steps. As engineers, we write code in different programming languages. All these programming languages have their own grammar, which mandates the syntax and semantics that we have to use in order to be productive upon it. So the first step is the abstract syntax tree, or the first phase of compilation is abstract syntax tree. As we write code, the compiler measures as to whether our code adheres to the grammar defined by the programming language. So as presented on the slide, you have operands and operators. So on the far left, you see const answer is equal to 42. 42 is tagged as a numeric literal. Answer is an identifier. Const is a variable declaration. And then we have an operator, an assignment happening. After the first step, which is adherence to compile, the syntax tree is completed. The next is control flow. In our code, we have various conditions. Based on these conditions, there are various branch and bound loops that are established. So we typically use if else, while, go, break, and go to, depending on the programming language, to define the control flow. Typically, compilers use control flow to optimize your code. That is the sole purpose of the compiler, besides other purposes for optimizing and constructing fragments of your code. The third step is typically in code, we create data, we initialize data, and we pass data between functions. So the elements of data have scope in it. It's either global scope or local scope within a certain control block that you've defined. So the program dependence graph gives us sufficient information of how variables are initialized and they traverse through various functions in your code. Note that these three representations are sequenced or completed as various steps in the compilation process. These representations, or what they call as intermediate representations, are fairly interesting. So how can we effectively use it to extract security insights? This is what our chief scientist, Dr. Fabian Yamaguchi, did. He took these three very rich structures and unified them to create a versatile graph format, which he called as code property graph in his PhD thesis. Having this unified representation at our dispense enables us to ask intelligent questions from a security perspective. Because as we noticed in the prior slide, when we get into the mind of an attacker, they're identifying ways or front doors from your web page into your application, thereafter to your host, and then the network, eventually leading to your data. So there are paths. There are various paths in the code that they're trying to figure out. The various weaknesses in your code that they're trying to exploit. So having this graph at our dispense helps us get into the mental model of the attacker and ask intelligent questions to identify inherent vulnerabilities in the code. Given that this is a layered fabric, different parts of the fabric represent syntax, control, and semantics. The call graph, meaning how data flows through your code. And then, like we looked at and observed at the map, you have a higher level path, and then as you take detours, there are subpaths. So how can we lift up and understand higher level flows from point of initiation to point of lookup at external resources like database, file systems, etc. And finally, How can we apply policies upon these high-level flows in order to suss out weaknesses or vulnerabilities that might exist in your code? This is the point at which Ocular was born. Ocular is an interactive query interface that helps us query this intelligent unified graph that we've created at ShiftLeft. This is a tool that can make the work of a security analyst or an AppSec team or developers very effective and efficient because it provides powerful querying capabilities to identify vulnerable conditions. But prior to understanding vulnerable conditions, we need to understand the structure of the application. Because as engineers, we code at high velocity. And with the advent of DevOps, our code is deployed even faster. So with these two fast motions, often security gets left behind. So we need a system to identify what our risk is at based on the attack surface of our application. And thereafter, we need to compare the evolution of our application version to version to understand its security posture and also understand if you're heading in a positive or a negative drift. So given that we spoke of the graph and the map, let us buckle up and navigate this very simple code snippet using Ocular. I want to give you a very quick overview of this code snippet. It's a very simple, innocuous code that represents a typical workflow, which is web-based. Note that there is a method called as doGet that accepts an HTTP request and produces an HTTP response. Consumers use our web page, and that web page in turn interacts or calls this function doGet. Now, if we glance at this code, from the request, we are extracting the login and password. We are crafting or concatenating a string, and thereafter applying that string to a SQL statement, looking up the database, and qualifying if the user exists. Now we have a control flow, which we spoke of earlier, where if the user exists, we populate a user object, we set a cookie, and then we forward the user to the next page, which thereafter proves that a session is established and the user is progressed into the value of your application. Now, if the user does not exist, we enter the second part of the branch and bound condition, and then we re-forward to the sign-in page with the appropriate message saying that the user failed to log in and does not exist. As you see, a very simple kind of code, very representative of how it looks like both from a legacy code perspective and even microservices that all of us write.